Okay, so I think we will start now. There is still maybe some other people joining in a bit later. So good afternoon, everyone. My name is Amir Shabar. I'm the chair of the Fauna Center of CMOS. And today we have Professor Kent Moore from the University of Toronto, who has agreed to give us a webinar on his work. Professor Moore's research interests include theoretical geophysical fluid dynamics, mesoscale meteorology, polar meteorology, high latitude air-sea ice interaction, physical oceanography, paleoclimatology, and others. He has published widely over 170 research papers in peer-reviewed literature, including Science, Nature, Climate Change, and Nature Communications. He's involved in the international collaboration that is seeking to understand today's topic is an evolving relationship of Nares Strait ice arches and the North Quarter, the Arctic most productive Polynya. Over to you, Professor.
Thank you. Just share my screen here. Yeah, so thank you for this opportunity to talk about the research that I'm doing in the Nares Strait region. And I want to first of all just acknowledge my collaborators on this work, both from Environment Canada, also U of T, and also from the University of Alberta. So we're all aware that Arctic sea ice is in decline. And so the area covered by sea ice has declined by about 40% over the instrumental record, which goes back to about 1979. And this is an animation. Hopefully it'll run. Sorry. Sorry, having trouble with my animations today. Here it goes. So this is an animation showing you essentially the minimum sea ice extent in the Arctic every year, starting with the advent of the microwave instrument in the 1970s. And so you can see that they've overlaid this graph showing essentially the ups and downs. So in the early part of the record, there was potentially, maybe 6.5, 7 million square kilometers of sea ice. Over, the period since then, we've seen this decline, this waxing and waning. Most of the sea ice loss has happened in the Western Arctic over here in the Beaufort and Chukchi Sea regions. The minimum sea ice extent that we've ever observed occurred in 2012 down here. And you can see that it rebounded after that. And so although there's this up and down from year to year, you can see this long-term trend. And so now we're potentially looking at perhaps 4 million square kilometers of sea ice during the September period of time. Sea ice is also getting younger and thinner. It turns out that thickness and age are correlated. Older ice tends to be thicker ice. This is just a picture I took a number of years ago doing some research off of the east coast of Greenland. This is first year ice. It's upwards of maybe 1 meter at a maximum thick. You can see in the background, these actually are icebergs. So these, of course, are land ice that has been discharged into the ocean. But this is the first year sea ice here. It's quite thin. It's also quite brittle. So there's lots of areas of open water kind of interspersed within the sea ice. This is multi-year ice off of East Greenland. And you can see that it's much more complicated, much thicker. One has these pressure ridges that build up. And this multi-year ice is it provides a very sort of suitable environment, very complex ecosystems that range from algae, which live on the bottom of these ice flows, up to polar bears who are at the top of the food pyramid. This is a schematic a number of years ago, essentially showing you how ice grows over time. And so this essentially is starting from essentially open water. So the first year we get ice growth, maybe 1.5 meters or so. Then of course it melts back in the summer. It grows the following year, so on and so on. You can see that the growth in the first year is larger than the growth in subsequent years. And that's because sea ice, of course, grows from the sea surface, which is at the bottom. And as the ice becomes thicker and thicker, it's more and more of an insulator. So it's harder for the cold Arctic air temperatures to actually freeze the ice at the bottom of the layer. And so over time, the growth becomes lesser and lesser. And this really shows you that essentially it takes a long time to get really thick ice. You can grow maybe a meter or a meter and a half of ice in a single year, but it might take many years to grow ice, which is 2 or 3 meters thick. So old ice is also takes a long time to grow. And that's one of the concerns because we're losing this old ice. And of course, it takes a long time for that old ice to be replenished. So this essentially shows you essentially over time, the sort of distribution of ice age in the Arctic. So again, if you go back to 1985, maybe 30% of the ice was first year ice, and maybe 30% was very old ice. And as see over time, we've lost all this old ice. And so now we're at a state where perhaps 60% of the ice is first year ice, and there's much, much less multi-year ice. So we're losing this very old ice out of the Arctic. This is another way to show that. This is a schematic of sea ice age back in 1984. And this shows you essentially at that point in time, there's about 2.5 million square kilometers of ice that was older than 4 years. This white stuff is the ice, which is older than 4 years. Jump forward to 2019, you can see now we're less than 500,000 square kilometers of this old ice. And you can see that just the dramatic retreat of this. So essentially, so what we're really doing is that as in addition to this loss of sea ice over time, we're also replacing essentially very old ice in the Arctic with ice which is just 1 year old or so. And so the only remaining really old ice in the Arctic is now here up against the coast of northern Greenland, and then of course the Canadian Arctic archipelago. This is the place where the oldest and thickest ice is on the planet actually. And this area is known as the last ice area right in here. So why is the ice so thick in the last ice area? This is a schematic of ice motion and ice thickness. And there's a couple of circulations we should be aware of. There's this thing called the Beaufort Gyre in the Western Arctic, which essentially is this anticyclonic circulation here. There's also what's known as the transpolar drift, which moves essentially from Siberia across to Nares Strait. And some of the ice, which is entrained in the Beaufort Gyre, gets ejected into the transpolar drift and then shoots out down here through Nares Strait. There's also outflow that comes down through Nares Strait and also the Canadian Arctic archipelago in here. And this black area here is the area which has the thickest ice in the Arctic. I think this is 4 meters thick here. And you can see that this is an area where there's convergence. So all this, the Beaufort Gyre tends to move in here. And so this is an area where there's a net convergence of ice, and the ice tends to remain in this area. And that's essentially why it becomes all thick, because essentially there's this convergence, and also the ice tends to remain in this area. So it just thickens over time. This is a scenario moving forward of what sea ice extent will be. So again, these are various scenarios with respect to emissions. This is historical data here. And these are the observed observations right in here. This is 1 million square kilometers down here. We're at about 4 million square kilometers now. 1 million square kilometers is what we define as being ice-free. So when people talk about an ice-free Arctic in the summer, they're really talking about sea ice extent less than 1 million square kilometers. So that's what's going to happen there. And you can see, depending on the scenario, sometime in the early part of the century or the later part of the century, we'll reach this 1 million square kilometer threshold. And that will then be a time when the Arctic is defined to be ice-free. But of course, there's still sea ice in the Arctic. Of course, if we get our act together and we get to some of these emission scenarios where we essentially, if you like, reduce our carbon emissions, you can see that the sea ice stabilizes at much, much higher levels. But under these sort of increasing greenhouse gas emission scenarios, we will sometime in the later part of the century reach this 1 million square kilometer limit. And that'll be the only ice that remains in the Arctic during the summer. And this is a schematic of what this last ice area looks like in the mid part of the 21st century. And so this is the area of the old and thick ice that will remain. And of course, this will then act as a refuge for ice-dependent species moving into the 21st century. And so this is an area of great importance. And of course, you can see that Canada essentially has a large portion of this last ice area, which is under our control. What have we done? The Canadian government in 2019 announced the creation of this area called the Tuva-Tuchitik Marine Protected Area. This is Inuit for the place where ice never melts. And you can see that it encompasses a large part of the Canadian last ice area. So in fact, we have moved to protect this region, which means there'll be no offshore development activities and restricted commercial activities occurring in this region moving forward. So that's a good first step. But of course, I think much more important step, of course, is to get to the point where we don't need to worry about the last ice area and we constrain our emissions so that sea ice remains in the Arctic. So I want to focus now on Nares Strait, which is, again, is one of these areas where sea ice from this very thick and old region leaves the Arctic. There was a concept back in the 19th century that there was a open polar sea. If you got north of the ice, there was this region where it was open. I'm not 100% sure exactly why they thought it would be open. And there were essentially three, if you like, proposed ways to get to this open sea. One was up through Bering Strait. The other one was up through essentially between Spitsbergen and Novaya Zemlya. This, of course, is where the Gulf Stream moves up. And I think the idea was that this Gulf Stream water got up here and, of course, led to this area of open water. The other area turns out to be Nares Strait, right up through here. Sorry. And in fact, it was a lot of expeditions in the 19th century tried to get to the open polar sea by moving up here through Nares Strait, which is quite interesting because that means there's a huge wealth of historical knowledge as to ice conditions in this region. For instance, Hall was the leader of this expedition called the Polaris Expedition. It was rather a bit of a disaster. Hall was poisoned, we think, by his chief science officer, Bessels here. He was buried in Hall Basin, but at least if we jump to sort of those sorts of things, one of the important observations that they made was that Hall Basin, which again is one of these areas in the northern part of Nares Strait, was never entirely frozen during the winter. And there was always open water present and wind-driven mobile ice was observed. So even in the midst of the winter, there appeared to be an idea that was motion in this region, which is quite interesting. Sir George Nares, who the strait is named after, was the first person to get right through the strait. And eventually he was blocked by the very thick ice north of Nares Strait in the Lincoln Sea. And this is a picture of his ship, the Alert, in pack ice along Nares Strait. At the southern end of Nares Strait, there's a recurring Polynya known as the North Water, or the Pico-Larswak, which is West Greenlandic for great upwelling. And this is a really important region. It's the largest Polynya in the Arctic, and it's also the most productive Polynya in the Arctic. It sustains a number of Inuit communities, Grise Fjord, Kanak, and a couple of other villages on the Greenlandic side. And of course, there's many species of marine mammals, beluga whales, seals, polar bears, walruses all use this area, as well as seabirds. So it's a really important area, very, very productive. And it's been suggested that the presence of an arch along Nares Strait is required for the existence of the now. And so this is a satellite image, I think, from 2018, showing an arch. As we'll talk about in this lecture, these arches form most winters along Nares Strait. They're quite remarkable features. This arch can be upwards of 100 kilometers in length, and it remains stable for months at a time. And you can see that once the arch is present here, this is the open water of the North Water downstream of the ice arch. And so there is some connection between the ice arch and the North Water. This is an image taken early in the year, and you can see there's a very low sun angle. You see the shadows. So there's really steep topography in this region. Well, you can just see the shadows here. This shows you in Evans just how steep some of the topography is in the Nares Strait region, which will play a role, it turns out, in the North Water formation, also potentially the arch as well. So in this talk, I'll use a variety of data sets. I'll use some reanalysis data sets, ERA5. There's an operational analysis from the ECMWF, as well as a recent regional reanalysis by the Europeans, which is called CARA, the Copernicus Arctic Regional Reanalysis. And it's quite interesting. It has a resolution of 2.5 kilometers. And it turns out that the strait is very, very narrow. And so to capture the winds along the strait, we require very high resolution. And the CARA has that resolution. We'll also look at sea ice concentration and motion data, both from passive and active microwave data. Sea ice thickness from this merged CMOS Cryosat-2 instrument. Chlorophyll A will look at primary productivity. There's automatic weather station data in the region, which unfortunately we'll be able to talk about today, but we have done that to validate some of our wind fields. And also, I'll briefly talk about an ocean model data from the NEMO LIM2 run known as ANA 12, which has about 4-kilometer resolution within Nares Strait. So one of the challenges, and this was an article written a couple of years ago, is that there's this concern that these arches, as we'll talk about in this lecture, are becoming leaky, and that allows the potential for a lot of this ice, which is old and thick ice in the last ice area, to exit down through Nares Strait. So one of the reasons why the last ice area may not be as stable as we think is that there is this, as we'll show, enhanced export of sea ice down through Nares Strait. And that's because the arches that form along Nares Strait aren't forming as often or as long as they did in the past. So again, this is just the topography of the Nares Strait region. The Lincoln Sea is up here, the Arctic Ocean, north and Baffin Bay here. The North Water forms in this region right here. And one way that we measure sea ice motion along Nares Strait is by looking at a flux gate here. And by measuring essentially the flux of ice through this gate, we can essentially determine how much ice is leaving the Arctic down through Nares Strait. You can see the topography here. There can be regions where maybe half a kilometer to a kilometer high on either side. And this is very, very high topography. And that again acts to channel the winds down through Nares Strait. So how do we measure ice along Nares Strait? The region's harsh, remote, difficult to measure directly, but we can use space-based synthetic aperture radar that's able to track individual ice flows, just distinguish them, and then by tracking their motion, we can estimate the transport of sea ice along Nares Strait. This gives you an example. This is a Sentinel-1 image from December 3rd, 2021. This is Northern Ellesmere Island. This is Northern Greenland here. This is Nares Strait down through here. And the SAR image has very high spatial resolution. You can identify individual ice flows. So this is the situation on December 3rd. This is the situation on December 7th. And just jumping back and forth, you can see that some of these flows have moved, right? In particular, just focusing on this one here, you can see that it's moved southwards, okay? And so Steve Howlett and Mike Brady have an automatic feature tracking algorithm at Environment Canada, and so they can look at these sequential images and then track the ice flows. And if you do that, this is what you get. So this essentially is the ice motion between those 2 days. You can see that we have this motion here, and then it accelerates as it moves down through Nares Strait here. So the ice motion on these days can be upwards of 10 kilometers per day down in this region, lesser up here. So we have Sentinel-1 was launched in 2016. So we have from 2016 onwards, we can essentially measure the ice motion down through Nares Strait, and I'll talk about that today. So what's really interesting about this ice transport is it's highly seasonal. So there's a typical period during the winter when the transport actually stops, okay? And this is essentially one of these, this across this ice gate. This is the ice area flux we've measured in square kilometers per day. So on a good day, you can get 1,000 square kilometers of sea ice moving down through Nares Strait. Positive means the motion is towards the south. And what's interesting is there actually are times when motion is towards the north. So the ice actually is moving northwards into Lincoln Sea, not southwards down through Nares Strait. And what's interesting, you can see this is the December into January, into February, and then suddenly the transport stops. Okay, and that's because an arch is present. And as I'll show you in a minute, once this arch is present, it stops the ice transport southwards. In this particular year, the arc remains stable until early part of late June, early July, where suddenly it collapses. I'll show you, and then the transport picked up again. So we can see that when the arch is present, we're not losing any of this ice down through Nares Strait. And so the concern is, as I'll show you, when the arch isn't present, we have this transport through the whole winter. And that means, of course, that more ice is leaving the last ice area in these years when arches don't form. So again, I just want to show you again a sequence of images showing you the formation of one of these arches. This is a southern arch. So that now we're looking at the southern part of Nares Strait. Again, this is Ellesmere Island. This is Greenland here. And I'll just show you a sequence here. You just track some of these flows. See the ice is moving southwards. And suddenly, right, the motion stops. This is the arch. The arch had formed over a few periods of days. It's still the ice still remains moving southwards, but north of the arch, the ice becomes stationary. So again, just look at this here again. You can see the ice moving southwards. This is the arch starting to form. The ice still fluxes southwards, but now the arch is formed and there's no motion north of the arch. So the motion is stopped. Okay. And eventually, after a few days, essentially all the ice that was sort of present has been fluxed southwards. And this is when you have essentially the start of open water within the North Water here. Okay. And again, these arches can be upwards of 100 kilometers in length. They're really quite amazing structures. I just want to show you some visible images showing you this arch through the seasons. So here again, we're looking at Ellesmere Island. This is Northwest Greenland. This is Kane Basin here. Lincoln Sea is up towards this direction here. This is March. So the sun returns in early March. This is one of the first sort of times of the year where we can see things in the North Water. And there's the arch right there. Into April, arch is still there. You can start seeing some areas where it's starting to brown, right? This is where the snow is starting to melt back. We're moving into the spring here. May, again, you can now see much larger areas of brown. Arch is still there. June, again, now you've got large areas of look at Northwest Greenland here. Essentially, it's now all the snow is melted. The arch is still there. You can start seeing bits start to break off. There's a bit there which is broken off. This is a few days later. You can now start to see that the ice is getting to be quite unstable. There's melt ponds. You can see some melt ponds have developed in the ice in here. And you see some cracks starting to develop. And then a few days later, the arch has collapsed. You can now see this, all this ice is now starting to move southwards again. So now we're getting open water. To the north, the ice is fluxing southwards. So these arches are they do change slightly over time. You can see slight changes in the shape of the arch. But what's remarkable is the stability of that for 6 months or so. That arch remains stable, and then it suddenly collapses and the ice moves southwards once again. This again is from 2020. This actually is a different satellite. This is a Sentinel-2, which has a resolution of 10 meters. The MODIS images had resolutions of 100 meters or so. And so this is just before the arch collapsed in 2020. You can see there's a crack starting to develop there. You can see the melt ponds back here. And then after the arch collapsed, all this ice is fluxing southwards into northern Baffin Bay with open water now starting to develop within Kane Basin. But what I want to draw your attention to is this little area over here of open water, which is distinct from the North Water. And here's just a sequence of images showing that this region, for a large period of time during the spring, it has open water present. This is Flagler Bay right in here, and this is known as the Flagler Bay Polynya. So the question is that this seems to be a persistent feature. If you go most winters, you can see it there. Has it been noticed before? And of course, it has. It turns out that Otto Sverdrup, who was Nansen's graduate student, explored this area in the early part of the 20th century. And then there was an expedition from the Oxford University run by Edward Shackleton, who was the son of the famous Shackleton. And he explored this region in the 1930s. And this is a map showing essentially the Flagler Bay Polynya. So again, here's Kane Basin. Here's the North Water. This is Flagler Bay here, and that's the Polynya sitting right there. It turns out the Mounties surprisingly had a station here in the 1930s. And in fact, it was this essentially station that the Shackleton used when he was in this region in the 1930s. So again, Sverdrup explored this region. He suggested that he found lots of artifacts in this region, which suggests there was a long-term settlement in this region. Again, then this Oxford University expedition spent time here. Edward Shackleton in his diary made the following comments. We descended again to the smooth ice of the Flagler Fjord. After several hours, he reached the narrow bottleneck at the entrance of the fjord. Stachys, who was one of his Inuit companions, were sleepy, and they were almost onto the new thin ice where the tide race swirled before they realized it. And later on, he says, in the meantime, the open water on which we had relied on for seal had frozen over. So they actually were talking about the Flagler Bay Polynya right here. So from their description, it looks like it's tidally forced. We think probably what's happening is there's some warm Atlantic water that gets up into this region. There's some sort of tidal race through here, and that brings the water up towards the surface and it opens up. It turns out this area was excavated in the 1970s, and it confirmed what Sverdrup had mentioned, that this site had been occupied for over 4,000 years. And what we think is what's happened is that this area was ready availability of marine mammals, and the Inuit would use this area to hunt. It's probably safer to hunt in the Flagler Bay Polynya than in the North Water, because again, it's just smaller and probably more not quite as exposed. So it's kind of interesting, again, the history of this region and how settlements have gone back for thousands of years. And again, Shackleton's description suggests this Polynya is associated with tidal currents in the region. I want to talk about this event which happened in 2017. So we talked about before how most of the time the ice area flux is southwards, which means the ice is moving southwards, but occasionally it can reverse. And so we're interested in knowing what these reversals look like. And this is a time series from the 1st of November to the middle of December 2017. The red curve is the ice area flux deduced from the Sentinel-1 data, and the blue curve is from this NEMO Anna 12 run. And you can see that there's two events of interest. There's this peak north-southward transport around the 13th of November, which again, the NEMO captured. And also this northward flux event where again, the ice reversed direction, it went up towards the Lincoln Sea around the 23rd of November. And again, NEMO captured this one as well. So we're kind of interested in knowing what caused this, first of all, what caused this reversal? And also what were the ice conditions like during this case? So these are again, our ice motion data on November 13th. You can see we have this very, very active transport southwards, ice motions of multiple tens of kilometers per day, fluxing southwards across the strait. So that's this event right here. And then a few days later, the ice reverses direction and moves northwards, again with ice motion of a few tens of kilometers per day. So this is the transport southwards. This is the transport northwards. So this transport is highly variable, and within a week, it can reverse direction. If you look at the ice concentration, this is the mean ice concentration in November. And you can see there's close to 100% ice cover in this region. This is the 13th of November when the ice is moving southwards. You can see some areas of reduced ice concentration in Lincoln Sea. And that's probably these areas of open water where the reduced ice concentration, where the ice is quickly moving southwards, leaving areas of reduced ice concentration. So you can see those right in there. What's most remarkable is the November 23rd, which is this time when the ice motion reversed and it went north into Lincoln Sea. And you can see large areas of reduced ice concentration, even some areas of open water. So this is a time series. The mean amount of open water in this region is maybe 200 square kilometers. This is what happened in 2017. You can see that there was a minimum in ice concentration when the ice was moving southward. That makes sense. But what's more remarkable is this very large area of open water when the ice is moving northwards. This is the 95th percentile based on about 20 years worth of data. And so this actually is the largest amount of open water that has been observed in this region. And what's interesting is that when Bessels and the Polaris expedition overwintered, they overwintered somewhere in this region right here. So when Bessels was talking about this area of open water during their overwintering, they were probably talking about these reversals where the ice was moving northwards up into the Lincoln Sea. And so that's sort of an interesting confirmation of the observations that Bessels made almost 150 years ago. So this is actually pretty cool. So you can see how the ice is very dynamic in this region, even in the middle of winter, one can get these areas of open water happening. So what caused the reversal? These are the winds. This is the mean winds for November. This is from CARA, this 2.5 kilometer resolution product. And you can see that on average, the winds actually are towards the northeast in this region. But during the time when we had this large flux southwards, the winds were probably southwards and again, much higher, upwards of maybe 12 meters per second coming down here through Nares Strait. And then of course, on the 23rd, when we had the opposite happening, when the ice fluxed northwards, you can see this large area of enhanced motion, again, in excess of 12 meters per second, extending all the way up into the Lincoln Sea. So these ice reversals are associated with large scale changes. There was probably a region of low pressure over here, region of high pressure, which caused this anticyclonic motion here. And there's probably a region of low pressure that caused this one right here. If you look at a time series, again, of ice motion, positive is towards the north, negative is towards the south. And you can see that this is the strong southward transport on the 13th. Again, it was in excess, it was lower than the 5th percentile value, so quite an extreme event. And this is the northward event right here. So these events, we have this nice period of time, just in a few days, where we had extremes in both directions, both in ice motion and also in the winds. So it's, again, the winds play a really important role in driving ice motion along Nares Strait. Then I want to talk about this ice area flux and what it tells us about what's happening over time. And this is we use a technique that Ray Kwok developed back in 2010, when he used a time series of ice area flux using RadarSat and ENVISAT data. His data covers this period of time here, and we've now extended it using our Sentinel-1 data. And then we can combine these two time series to see how things have changed over time. To get the ice volume flux, we need to know thickness data. And so we've used PyMass to estimate thickness to get us the ice volume. And what I'm going to show you are annual averages over this period of time, starting in September and ending the following August. So this is the annual ice area flux. The red data is from Kwok. The blue data is from our study. And this is the average over the Kwok period. This is the average over our period of time here. And you can see there's lots of variability. 2007, as I'll talk about in a few minutes, was a very extreme year because, in fact, there was no ice arches formed that year. And this was, at least in the Kwok data, the largest ice transport that occurred. And so you look at our data here, you can see that on average, of course, our data is much shorter time length, but then that's obviously an issue. But you can see there appears to be an increase in the annual ice area flux recently compared to the past. This is PyMass ice thickness data, and you can see how during the Kwok period of time, the average ice thickness may have been 2.5 meters. Now it's about 1.7 meters. And so this is the thinning that's happened in the region. And then when you combine these two, you can get the ice volume transport. And you can see that because the ice is getting thinner compared to the Kwok period, even though the ice area flux is large, the ice volume flux isn't as large as the ice area flux, just because the ice is getting thinner. Still, it's about 150% increase in the annual ice volume flux. And again, you see that 2007 is an outlier here, where there was very, very large ice volume flux, upwards of 200 square kilometers in that year of ice left the Arctic along Nares Strait. If you now look in essentially the catalog of how long the ice arches have survived in days, this is a plot showing essentially data going back to essentially it's the Kwok period and our data here. It turns out 2019 was a year where, again, an ice arch didn't form. So we now have 2 years, 2007 and 2019. This is the data. If you just plot a linear fit to it, you can see there's a trend towards shorter duration arches. So the arches are getting shorter by about a week per year. So again, quite a dramatic reduction in the duration of time at which the arches occur. And of course, reduced time of arches present means more time for ice to transport southwards. So what I want to focus on now is this relationship between Nares Strait and the North Water, okay? And so again, if you read the literature, there's a consensus that the arch that forms at the southern end of Nares Strait is responsible for the formation of the now. It does two things. Once the arch is present, as we showed, no more transport of ice southwards. And then, of course, as there's very high winds that develop along Smith Sound. And so those Smith Sound winds essentially head back any ice that forms southwards. So the arch is thought to play a very fundamental role in the formation of the now. And of course, the thinning of the sea ice that we've seen is reducing the stability of these arches. And so therefore it's placing it in jeopardy of the now. And so the final thing I want to talk about is that what is the structure of the now in the absence of a southern ice arch? So this is the complete record of ice area fluxes that we have, starting with Sentinel-1 data starting in November 2016, ending in June 2022. So again, positive means the transport is southwards, negative means the transport is northwards. And you can see again, large changes from year to year. This is a year where a northern arch formed, and although the ice motion was reduced, there was still this back and forth happening as we've seen all throughout the winter. And then the arch collapsed in early May and suddenly the ice fluxes went up again. This is 2018, large transport through to March, and then an arch formed and the arch remained stable for a period of time. In 2019, you can see there was no reduction. The ice area flux remained large throughout the whole winter. This is a winter where no arch formed. 2020, again, an arch formed. You can see that arches are not all the same. This year, there was always some back and forth. This arch was much more stable. So the transport actually went to zero. 2021, again, an arch formed, but it was one again where there was still transport through the winter. And then 2022, which is last winter, no arch formed. Okay, so in this period of sort of 6 years, we have essentially one winter where a northern arch formed, 3 winters where a southern arch formed, and then 2 winters where no arch formed. And if you just look at the ice concentration, again, I'm focusing on May. This is the ice concentration in May for these 6 years. This is the year where a northern arch formed. And you can see that during this winter, there was open water all the way down through Nares Strait, down into the North Water, which is right in here. 2018, a southern arch formed, and you can see there's 100% ice cover in the northern part of Nares Strait. This is the ice arch there, and then open water south of the ice arch. 2019, no arch formed. Again, you can see open water through Kennedy Channel, down into the North Water. 2020, an arch formed. Again, very similar to 2018, 100% ice cover north of the arch, and then open water to the south. 2021, again, another southern arch formed, again, very, very similar. And this is 2022, where no arch formed. And again, one had open water in Kennedy Channel. There was not so much open water in Kane Basin, and then open water over the North Water. So again, there's lots of variability from year to year, but it looks like there is this common signal that when you don't have a southern arch present, you get open water along Kennedy Channel, and over the North Water, it appears that there's open water in the absence or in the presence of an arch. So it turns out, I'm using the AMSR2 data here. So that data starts in 2003. And this is the categorization of all the winters from 2003 to 2022. So again, the predominant thing is a southern arch. This is 2007, where no arch formed. 2009 and 2010 had northern arches. Again, southern arches, a northern arch in 2017, no arch in 2019, and no arch in 2022. So we have essentially almost 20 years worth of data. And so what I did to try to sort of quantify or put some sort of like get some idea of what's happening in these various categories is I looked at winters where there was a southern arch present, winters where there was a northern arch present, or winters where there was no arch present. And if you composite the data, this is what you get. This is the southern arch. And again, it looks very similar to those cases that I showed you. 100% ice cover in the northern part of Nares Strait, open water over the North Water. The arch doesn't show up as clear as it does in any given year, because of course the position can vary from year to year. So the arch is this kind of diffuse region where the concentrations go from less than 25 to greater than 75. This is a northern arch. You can see there's the presence of the northern arch right there. Again, reduced ice cover all the way along through Nares Strait. This is the no arch case. And again, you can see there are some similarities and some differences between these two. But one tends to get open water in Kane Basin, as well as open water over the north water. So what I want to do is I want to essentially collapse these three cases down into two, and the two cases will be essentially either a southern arch present or no southern arch present. Okay, so these are these two cases here. And again, you can see when you collapse the northern arch and the no southern arch cases together, you can see that you get essentially this region of open water over Kennedy Channel and the northern part of Kane Basin, as well as open water over the north water. There are some differences. There's more ice cover in the western part of the north water when you have no southern arch present. And that's because we do have ice moving southwards, very thick ice. And so it tends to hug the west coast because of the ocean currents. And so you do tend to get some thicker ice, more ice on the western side, but there is open water present in both of these scenarios. If you look at thickness data, you can again see in the southern arch case, ice thicknesses in the northern part of Nares Strait are between 1.5 and 2 meters. And then over the north water, ice is much, much thinner, less than half, 20.2 meters in here, with thick ice along the western coast of the north water. This is in the absence of a southern arch. And you can see again, in addition to having reduced ice concentration in this region, one has thinner ice. Okay, the ice does tend to thicken in Kane Basin. And that's, I think, because as the ice moves southwards, it's kind of gets backed up because there's this constriction right here. And so there's this dynamical thickening, we think, of ice over Kane Basin. Sorry. Sorry, that animation stopped. Anyway, I want to finish up by looking at chlorophyll A, which is you can get from ocean color remote sensing. And this shows you again the composite monthly mean chlorophyll A during May in the presence of an arch and the absence of an arch. And of course, the first thing you see is that when you don't have an arch present, there's sea ice in the northern part of Nares Strait, so there's no productivity happening. Over the now, you can get upwards of 2 milligrams per meter cubed. And if you look at what happens when an arch is not present, now because there's open water all along Nares Strait, there is low productivity, but nevertheless productivity happening along the strait. And then over the now again, there is higher levels of productivity. I wouldn't make too much of this difference between 2 and 3. It may be just the number of cases. Again, we don't have, there's only 6 years with no southern arch present. There's about 12 years where there's a southern arch present. So this could just be sampling issues here. But the point is that there's a similar amount of productivity happening over the now in the absence or in the presence of a southern arch. So just to conclude then, the Arctic is seeing this loss of sea ice as well as an accelerated loss of old and thick ice. North of Canada and Greenland has the oldest and thickest ice on the planet. And as we move sometime during the middle part of the century to an ice-free Arctic, this area will remain ice covered throughout the year, and that will provide a refuge for ice-dependent species moving forward. There's evidence that the thinning ice is also increasing the transport of this very old and thick ice along Nares Strait, as well as weakening the arches that form in the region. And this suggests the last ice area may not be as stable as we thought because there is this increased loss of ice coming down through Nares Strait. If you focus on the north water, it's situated at the southern end of Nares Strait, and it's been proposed that the presence of an arch is required for its formation. And there are concerns, again, moving forward, if the arches don't form, or if they're short-lived, the now and its complex ecosystem may be threatened. If we look at composites of the sea ice and primary productivity, with and without the absence of an arch, we come up with a different scenario. This suggests that at least with respect to ice concentration, and at least current productivity, the now will be stable. So it doesn't require a southern arch for the now to be ice-free. And the reason is quite simple, is that even in the absence of an arch, one still has those very strong winds that blow southwards along Nares Strait. And so they will continue to affect any sea ice that comes south out of the area of the now. So the now will remain, at least according to this study, stable moving to the future. And of course, there's other things happening. The sea surface temperatures are warming in the region. There's evidence that the primary productivity is decreasing, primarily because the ocean is getting warmer. There's changes in salinity, changes in stability. All those things impact the productivity of the now. And so the now still be under pressure, but I think at least the results of this study show that it's not as dire as we once thought, and that even if arches don't form, the now will still survive in something similar to its present state. Thank you very much. I'm happy to answer any questions that people have.
So there's one question on the chat. It says, why is the North water biologically productive, if not because of the Southern Arch?
So there is upwelling that happens in the region. Sorry, stop sharing. There is upwelling that happens in the region, and so that essentially brings nutrients to the surface. Of course, the open water doesn't hurt because, again, the open water means that one can have this productivity happening earlier in the season. And so I think it's a combination of the open water and also the upwelling of nutrients that provide for the productivity of the region.
Any other questions?
Mike had another question about the Flagler Bay Polynya. That's a really good question. So, of course, it's getting kind of small, so it's not clear that we can resolve the winds in the region, but it doesn't appear that it's wind driven. It appears that it is essentially driven by the we think by the upwelling of warm Atlantic water in a tidal race. So that's an open question, but we think it is actually oceanographically forced, not forced by the atmosphere.
Okay, another question is, when we talk about the formation location of the Southern Arch, for example, is there a large variation in where specifically the arch forms year to year?
Yeah, that's a really good question. So there is lots of variability. Maybe I'll just share my screen one more time and go back to, sorry, I hate doing this, but I will. Yeah, so it tends to form sort of, so this is the narrowest, this is Smith Sound. It tends to be the narrowest part of Nares Strait. So it tends to form just north of Smith Sound. And so these years it all sort of, you can see some years is getting a bit farther north. Here it's quite a bit farther south. It can extend as far, this is called Pym Island right here. Some years it can extend way into Kane Basin. And we don't really understand why some years the arch is kind of shallow and some years it's actually quite deep. So I don't think we understand that. I'm not an ice geology person, and so this is kind of beyond my area of expertise. But it must have something to do with the thickness of the ice, and we're trying to understand this, why it is that some years, the arch extends far into Nares Strait, far into Kane Basin, and some years it doesn't. But we don't know yet. But it's a very interesting question to why that happens. The arch can also evolve over the period of the winter. I think I showed you a little example there where there was some slight changes during the winter. There can be times when some of the ice breaks off of the arch. Probably a combination of winds and also tidal forcing, that causes bits to break off. So there can be little bits broken off, but the core of the arch can remain stable for months at a time, which is, I think, really quite remarkable.
Okay. I don't see any other questions. Oh, yes, there is. Why are the two cases, Northern Arch versus no arch, similar with respect to, with respect to ice to the south?
That's a really good question. So I think there are some differences in the two cases. So if we look at a case of a northern arch, as I look at 2017, then of course, when an arch forms here, all the very thick ice is kept north of Nares Strait, and so ice does form. Of course, it's the winter, so ice is always forming along the strait. Of course, it's very, very thin ice, and that ice tends to be advected southwards. So it's in a case of a northern arch, one has thin ice present in the arch in the strait, which then moves southwards. When no arch forms, like let's look at 2019, then what we have is we have essentially this thick multi-year ice moving southwards along the strait. So I was quite surprised, frankly, when if you look at these 2 years, it's quite similar with respect to concentration. There is more open water present in 2017 compared to 2019, but both of them have open water in both northern Kennedy Channel and then northern Kane Basin, as well as over the now. So it turns out there's 2 regions of the strait that are very narrow. One of them is Kennedy Channel. The other one is Kane Basin right here. And so if you look at the winds, and unfortunately I didn't have time to show the winds. So the winds tend to be very strong in Kennedy Channel, as well as in Smith Sound. And that's mostly because these are very narrow regions. And so and of course we have steep topography on either side. And so the air is forced to essentially move through a much narrower channel, and that leads to an acceleration. So what I think is happening over both the northern Kennedy Channel as well as the North Water is that one has these very strong winds, and any ice that's present is being advected southwards. Okay, so we get open water both in Kennedy Channel as well as over the now. So the point is, you just compare these 2 winters. This has an arch, this one doesn't have an arch. So again, the winds are strong enough to blow this ice southwards, this multi-year ice. If you look carefully, you can see there's more ice along the western boundary here than here. And of course, that's a symptom of this very thick ice, which is moving southwards. But over the central part of Smith Sound, the winds are strong enough, at least that's the hypothesis, to even blow multi-year ice southwards and keep it open during the period of time. So that's the basic hypothesis that we have. It's the very strong winds that blow along Nares Strait, primarily in the location of Kennedy Channel, as well as in location of Smith Sound, that are able to advect this ice southwards. And so you get open water, whether an arch is present or not.
Okay, so I don't see any further questions. So I would like to thank you very much for a very interesting seminar. I learned a lot, I think, in the Arctic. I'm a circulation guy, so I look at large-scale circulation. I don't necessarily look at ice and so on, but it was very interesting. And I thank you for joining and giving us a very interesting seminar.
Thank you very much. Thank you. Bye now.
Bye.